2000 and 2002, and was associate editor of the journal on Magnetics and Magnetic Material from 2010 and 2012. Is a Humboldt Fellow and also is an active communicator and journalist about science, political and social problems. It's a pleasure for us receiving you, Professor. Thank you.
Hello. Before they... okay, they put the slides in. Okay. Well, before starting the talk, I would like to say something about Professor Danai Kunka from the Institute of Microstructure Technology and the Karlsruhe Institute. Just this. Okay. Okay. From the Karlsruhe Institute of Technology, she is a co-author of this presentation, and we have a long-standing collaboration of several years, and part of the results we're showing here is a joint work between the University of Havana and the Karlsruhe Institute of Technology. What will I, okay, this works. What will I be talking today? And I hope there's enough time for that. Well, I'm going to show you a story about how can we discover patterns instead of recognizing patterns. There's a big difference between the two of them. And then we will show how we're doing that using entropic measures. And well, we will go through several examples and how this is done and so on. So this is the outline of the talk. You can see it there. I don't have to repeat it. And those are the things we are going to touch upon this talk. So the question is, how do we come to recognize patterns? And we're talking about recognizing patterns, and we're making the difference between recognizing patterns and, or I would say, discovering patterns, and between that and the fact that we are recognizing something. When we say we are recognizing something, and this is a bit, okay. When we say that we are recognizing something, what we mean is we have an idea of what we are looking for. So we say, for example, we have a number of persons, and we say, for example, we can ask ourselves the question, who is a mulatto there? And that means we have an idea what mulatto is. So we have what are the features of that pattern that we want to recognize. And that's what we are calling recognizing patterns. So we say, okay, the color of the screen is brown, or the hair is curly, or it has thick lips, and so on. So we have, before we are confronted with the data, we have an idea, we have a definition of what's the pattern we're looking for. And in contrast with that, when we are discovering a pattern, is we don't have the slightest idea which patterns we are going to find in the data. So we don't have a predefined definition of what we're looking for. We are looking for patterns, and that's what we are calling discovering a pattern. So you have a number of faces there, for example, and you say, is there a pattern here? Any pattern. Is there something there that repeats from one face to the other and it's common to all the faces? And that's what we are calling about discovering patterns. And of course, as is usual in science, the devil works in the details. So we have to ask ourselves what we're looking for. We have to distinguish between what is noise, what is a random accident, and what are regularities in the data. And a lot of other questions, but let's say this captures the idea of what I'm talking about. So discovering pattern is a much more difficult endeavor than recognizing a pattern. And we've been, when I say we I mean humankind have been, over the years and over the centuries, we have been very much keen to recognize patterns in nature. And that, of course, from evolutionary pressure, we did it at the beginning because we needed to survive, and from there on we have it somehow hardwired in our brain, and we still don't have a whole complete answer about that. So even quite late paper, I mean quite recent paper from 2000 and something, was asking Crutchfield, which is an American scientist from the University of California, was asking itself, what is a pattern? How can we recognize a pattern that we never seen before. And trying to, let's say, reduce the question from this general framework to a much more tractable idea. He said, moreover, everyday experience shows us that nature inherently organized, it generates pattern. Pattern is as much the fabric of life as life is unpredictability. And that's very important because, again, as we human beings, from the evolutionary perspective, have been coded to see patterns from a survival point of view. When we used to live in the open air and there were quite aggressive animals out there, we used to see patterns where there was no patterns. And that we have it until today. In the dark, we are always wary because if we hear a sound, we immediately are alert. And that's, we are recognizing a pattern there which is not there, it's just an accident, but our brain are constantly forming patterns in its head because it was a survival thing and it's still coded in a brain. So we have to be careful, and now, fortunately enough, we don't live in the open air. We don't have, at least we don't have aggressive animals that are not ourselves threatening us. So we have to somehow, we have to go beyond our national tendency to see patterns where patterns are not. So we need some objective, we need something which has some objectivity of how to recognize pattern which is not a matter of our own brain coding. So we need to put some way of doing that. But before we do that, let me be a bit more simple and say, what do we find normally, let's say, what do we find normally in our everyday life or in nature? We have in one extreme, we have what we call periodic order. In a periodic order, everything is a pattern. You have something which is repeating itself. So you have very clearly, you recognize their pattern, even if you can discover the pattern, even if you weren't looking for it, because you see something that repeats itself exactly. And that's what we call a periodic pattern. And this is not complex at all. If I want to describe periodicity, it's very simple. I can just say, for example, there in the sequence of 1 and 0, I can say there's 1, 1, 0, 0 repeated L times. And that's the whole description of the system. So it didn't took me much words to describe the whole system. It just with a few words I could describe the whole thing that was going there. In the other side, in the other extreme, we have completely randomness, like throwing a dice. So when we're throwing a dice, we don't have any idea what's coming afterwards. So it doesn't matter how much we saw before, it doesn't matter how much of the past we are seeing, we are still as unable as somebody who never saw any sequence to guess what's the next number. The next number has a probability of 1/6. So if you have any sequence of L dice drawing, you will have a probability of having a particular sequence of numbers. That probability will be 6 to the minus L, and L is the length of that sequence you have there. So you have two extremes. You have the periodic and you have the random. And reality actually is much more interesting than that. In reality, you have some randomness, you have something which is unpredictable, and you have some pattern. And that's what the problem for us, not the problem for nature, comes. That how can we distinguish from the randomness and from the pattern, and how can we say that we have a pattern, and then after that find a law of that pattern. So the complexity of things are really in the middle of this, they call it the one bump graphic. Here is where things are happening, where you don't have periodicity, when you don't have random. To analyze this type of data, this type of systems, this was done, or this started to be done a long time ago, after the Second World War. It was Shannon, an engineer, who started what today we're calling information theory. And forget about the formula, just look into this. This is the so-called Shannon entropy. The main point about Shannon entropy is that it measures the average surprise when you're seeing something that you are characterizing from a statistical point of view. So if you have a number of possible outcomes and you have a probability for those possible outcomes, you calculate your average surprise in that way. That will be enough for what we're going to talk. in this, what we're going to say in this talk, so I won't go into it. This is not a whole conference about Shannon entropy, but this is our hero in this talk. Shannon entropy and all the derivatives measures you can come up out of the Shannon entropy. The first one of that will be the so-called entropy density. So how do we define this entropy density? If you have, we are here in a computer conference, so I will talk about in terms of a binary sequence, and we all know that the binary sequence is a representation of a sequence in any other number base. So if you make a partition of your sequence in blocks of length L, and now you say, what's the probability of finding a particular sequence of length L? Then you can define again a Shannon entropy like this. So this will be the probability of finding a particular sequence of length L, and you add up all those probabilities, and again you have here an average, you have here the Shannon entropy, which is the average surprise of finding any sequence in this sequence of 1 and zeros. And then if you just make a normalization out of the length of the whole sequence, and you go from L to, you make the limit to very huge L to infinity, then you get what is called the entropy density. And the entropy density is a measure of the reducible randomness of a system. That means after I take care of all the patterns in my system, what's the randomness that is left? What is that is irreducible, that I cannot explain in any way, that is a throwing of a dice or a coin or whatever? So that's what this entropy density is telling us. It also can have an interpretation in terms of what is the information production of a system, or again, what's the amount of dice throwing you have in a system. And the other measure we're going to use a lot is the so-called excess entropy, which was introduced with another name by Grasberg, which is a already very old person, but a very heavyweight in complex theory and chaos theory. And they introduced this excess entropy, and I won't go much into detail there, but I would just say that the excess entropy is a measure of the correlation between, and if we consider this kind of a temporal sequence, a temporal series, we will say how much can we know of the future if we know the past. And if this is considered to be an infinite sequence, doesn't matter where you make your cut. For an infinite sequence, any point will be the half. And I will say, if I know everything that happens from here to the left, how much can I guess of what's happening from here to the right? And that's what's called, or the excess entropy wants to measure that in some way. For those who know a bit about information theory, it's the mutual information between what we are calling here the past and the future. And that's, he's measuring correlations. And the nice thing about the excess entropy is that this is a number, and with a single number, you can measure correlations in all length scale. So in one, you have a measure which is entropy density, which is measuring randomness, and now you have one which is measuring correlations. He cannot tell you what are the correlations, what are the patterns. He can only tell you there is a correlation, there is a pattern there, or there are several patterns there. And building from there, we have what we call information distance. And information distance is, and here I get into what is probably more exciting for you. Information distance is the following. You have a sequence of 1 and 0 here, and you have another sequence of 1 and 0 here. And I will ask, what's the algorithmic relation between the two of them? And the answer came from the original work of Kolmogorov, and this has been developed a lot in what is called Kolmogorov complexity theory. And it says, is the length of the shortest program that can take you from this sequence to this sequence and vice versa. So it's not a pattern distance. It's not the so-called, for example, Hamming distance, which is in how much points the two sequences differ. What it's telling me is something more elaborate than that. It's telling me how much effort do I have to put in a computational sense from going from this sequence to this sequence and vice versa. I just take the smallest of the two. and that's what's called information distance. So these are our three main characters in the play I'm talking now. We have entropy density, we have excess entropy, and we have informational distance. So we are ready to start this adventure. First of all, just a simple example, just using these three measures, not much more than that. And that will be a tenet of the talk here. How can we take the most out of a data in the simplest way possible? And that's something we do in science every day. How can I say something about what I'm analyzing without using much more machinery than what I need? That's the core, what is called the Occam razor. So we did this. We have, well, this is just an example of one of the things we have done. You have here the RNA of tissues, and this is experimental tissues, where you had a number of healthy people and a number of people that had different types of cancer. And they were made this DNA analysis of it, and from that DNA analysis, you have the sequence of the DNA, and you have letters there. You make what is called a sorted list out of something which biologists people call pathway, and then from there, we made a binarization, well, not a binarization, a three-serization. May I say that? Well, I will say it anyway. You have three numbers, 0, 1, and -1. 0 means that a particular gene is not expressed. This is molecular biology jargon. For us, it's not important. I just say it so everybody can understand what I'm saying. The gene is not expressed. 1 means the gene is overexpressed, and -1 means the gene is underexpressed. For us, you have a sequence of three numbers, 0, 1, and -1 for every gene, and what it's telling me is that the gene are in three possible states. And from that sequence, we calculate entropy density, excess entropy, and information distance. And just what you are seeing here is we will be seeing that a lot in the talk. What you're seeing here is what we call a complexity map. What you see here is excess entropy and here entropy density of each of these tissues here. And this is the mean value because, well, okay, you do it a lot of times and you take the mean value of it. And unfortunately, this is not looking very well, but I will explain what's that. All this is published there, and you can find it in the talk, or you can go directly with the link to this QR. And what we're seeing here is that we can make a very robust classification between healthy people and the people with cancer. We are not using here any huge machinery. We are not using here artificial intelligence. We are not using here any sophisticated machinery of data processing. We're just calculating excess entropy, entropy density, in this case, just excess entropy and entropy density. And that's what you're seeing here. This is a dendrogram made out of the informational distance between the genes of every subject in the experiment. And the blue ones are the healthy ones, and the red are the cancer one, or vice versa. I really don't remember now. But that's not important. What you see is that they are very well segmented. And from that, we made a table of what was our success fraction in determining that you had cancer or not cancer. And furthermore, not only it was able to distinguish if you had cancer or not, it was able to distinguish which kind of cancer. You had all these letters here, which are quite cryptic, and just saying different types of cancer. So for example, we had for this type of cancer, we have a huge success rate, 99.7, and you can see here that the numbers are really shocking. And for the normal persons also, well, here you have a bit of a failure, but after that, you see that the numbers are quite good for every other type of cancer. So we are not only able to distinguish healthy people from cancer people, we are also able to distinguish which kind of cancer do they have there. Again, this is a distance matrix. This is a matrix of the distance of every gene to every other gene. If you just see a row of that, what we're seeing, every number here, which is in a grayscale, is telling you what's the difference between the gene of one of the patients with all the other ones, no? And you make a matrix out of it, and from the matrix, again, you can make a dendrogram. And the yellow there This is to distinguish between two types of cancer. The red, well, the black is normal people, healthy people. The red is people. These are two cancers which are very, very related between them. This is a kidney cancer, two types of kidney cancer. So from the DNA point of view, they are very similar. And yet, in spite of that, you see the red is one type of cancer, the yellow is the other type of cancer, and you see that there's a clear clustering. So we are able again to segment, to make a segmentation between those type of cancers, even if they are quite close one to the other. And for that we're using, again, we're not using any sophisticated machinery. We did a very, very simple discriminating criteria. We said, from a distant point of view, if you have a subject, you just count your nearest neighbor, and you make a majority rule. You say, if my nearest neighbor are of this kind, you are of the same kind. That's a simple rule we followed there. And with that, we had this very nice success rate I just showed you there. And now we go to another, let's say, we're getting more involved. We're going to analyze nonlinear couple oscillator. Why are we going to analyze nonlinear couple oscillators? Well, nonlinear couple oscillators, we will see it here. We will see it here when there are several models, and one of the most common models for brain activity is to consider that the brain is a huge number of oscillators which are coupled one with the other. So from that, let's say from that inspiration, people have been studying a lot of these couple oscillators. They are found everywhere in nature, from fireflies flashing in the night to whatever you tell me. It's kind of a universal model somehow. You tell me a problem, I will tell you which couple oscillator can describe your problem. And we will say why, I will say something about why that happens in that way. But why are we analyzing that? Well, what we are looking for here, and I will tell you why we're looking for that, is we are trying to see if couple oscillators can have computational capabilities. And for us, computational capabilities is not from the anthropocentric point of view. I'm not talking about computational capabilities directly in the sense that you have a computer, you put an input, you get an output of what you want him to do. We are talking that something has computational capability if it's able to store information, transmit information, and transform information. So any system, natural or not, that are capable of these three things, we say it has computational capability. We didn't come up with that definition. That's quite common in the literature of this kind of analysis. And why are we doing that? Well, people are trying to find computational models in nature that avoids the use of energy costly devices. We all know, or I suppose we all know, that one of the, let's say, practical problems of artificial intelligence right now is that with the current technology we have, it's energy unsustainable. As far as we're doing small applications in a small number of cases, we can do it. But when you go to the massive scale and you calculate the energy you need for that, you will see this is unfeasible with the current technology, with the current microchips. There's no way the number of computer clusters you need, the energy all this needs, if you're saying that you're going to use artificial intelligence in a massive scale to solve all our problems, humankind problems, today with the current technology we have, that's unfeasible from the energy point of view. So we are looking for models in nature that we can reduce the energy cost of what we are doing. And of course, the first thing you think about is the brain. We don't need that much energy, although we can be very hungry. We don't need that much energy to think. How can we emulate that? How can we make devices that don't need that much energy as today electronic devices to think like we do every day and we're doing right now? The other point is that any algorithmic models and all that we have been working with and all that we're seeing mostly even in this artificial intelligence trend is algorithmic models, and they can be as good as its logics. What does that mean? It means you tell the system what you want. It's centered in the person. We tell the system, I want you to make these calculations. Things don't work that way in nature. they are there, they are working, and we come and we take, it's the word that is used to say is we harvest. We harvest the information they are giving continuously. They are not doing something to please us. They're just doing things. And we come there and we harvest from there what we need from there. And of course, there's always the curiosity of humankind, so we always love to think out of the box. So that's why we're analyzing simple models that are somehow mimicking things that are happening in nature. And as we usually do in physics and other areas of science, we go from simple systems and we start to complicate systems. So we start with this very simple electronic circuit, which is called, which is governed by something which is called the Adler equation. Adler did it a lot of years ago in the 50s, 60s. He was doing, at that time they were looking for a feedback for this, for controls. And they had problems. Remember, at that time, no transistor, no integrated circuit. There were, the controls came crazy, and they were looking for feedbacks that could control let's say, inalambric controls. So he came up with this kind of circuit. This is the equation of the circuit. This is the phase. When you put this in an oscilloscope and you get a signal, this is the phase of the signal, and this is the equation of that. And my student yesterday talked about this. I won't go much into detail in it, just to say this is what is called the proper frequencies of the system, and this is the feedback strength. So this is the classical Adler equation. What you do from that is you make a couple. You say, I don't have just one oscillator, I have as many oscillators as I have, as I can, let's say n oscillators, and they are coupled in this way. And this was introduced by Alonso some years ago, and we jump into it. We say, okay, he made some kind of analysis of how this behaves. Remember, this is not only one equation. This I goes from 1 to n, and we analyze how the oscillators evolve in time. So let me picture what's going on here. You have a coupled oscillators, you have a lot of oscillators, you give them an input, you say, okay, each of these oscillators has an initial phase, and you let it run. And you say, let's see where he goes. And what are your control parameters? Your control parameters, again, is the intrinsic frequency, the self-feedback strength, and then you have this K, which is the strength of the coupling with the neighbors. And with that, the first thing you do, at least the first thing you do in physics, if you build something which we love and we call a phase diagram. And it means how does this behave when we are changing the control parameters. So I won't go much into details, it doesn't really make much sense, but you have here your gamma, which is your, remember, is your feedback strength, and you have your intrinsic frequency here, and what you are seeing here is what is the entropy density of the system after it runs for a long time, and red is when you have a big entropy density, 0 where you don't have any entropy density, and where is the banana? The banana is in the middle. And where is the middle here? Here and here. So that's what we want to explore. We don't want something that goes just to some regular kind of very predictable behavior. Everybody's 1, everybody's 0, or everybody's 1, 0, 1, 0, 1, 0, or whatever. We won't go to chaotic things in the sense of disorder. Chaotic is a chaotic word. You have to be careful when you use it. But I'm using it here in terms of disorder. You don't want to go to a disorder regime where it doesn't matter what you put there. At the end, you get something which is like throwing a dice. That's not useful. Where it's useful in parameter space is in this region and in this region. So that's the region we make an analysis of. This we call the needle region. Well, every time you see this, well, in this case it's not there, but that's where we publish all these results. So this is the called needle region there, and you see here the evolution of your oscillators in time. Time is in this direction. This here in this direction you have space, that means every oscillator. And what we're seeing here, how do they behave in each of these regions there? And I won't stop here because I want to go to the needle region. This is the needle region. And this is the behavior in the needle region in different points, and you can see something very interesting happen. There's a wavy pattern. This is not chaotic. This is not really periodic. This is something which we can just, from an intuitive point of view, we can say, some processing is going on there. if I put something here, it gets transmitted in time. Somehow the initial information is not lost. At the same time, this initial information is organized and it travels. So here we're having something that looks like that it has computing capability. And that's what we're looking for. So what's next? Well, what's next is how can we optimize that? And there comes a very interesting hypothesis that came in the 90s by Lanton, and then came Crutchfield, but the first guy was here, Lanton. And he came with a very interesting concept that is used today, and there's a lot of research there going on, which is called computation at the edge of chaos. And this hypothesis said that precisely in the regions where you go from any kind of order to chaotic, this border here, that's where things are really getting hot. And that hypothesis said that that's how the brain works, that our brain works in the edge between chaotic and ordered behavior. So we are always working in the edge of madness. We don't go to madness, and we're just in the edge of it. And that hypothesis says this is where really computational capability gets enhanced. And we ask ourselves, how could we capture that? And for example, here you see, these are papers quite recent. This is 2004, 2008. And what they're saying is they started to see if this was right, and they started to find that it seems this is not conclusive. It seems that yes, that the brain works at the edge of chaos. So how can we find if something is in the edge of chaos? And we came with the idea using our entropic measures. We said, we just find it by serendipity. We said, we started seeing how the entropic measures were behaving when we moved from the chaotic region to the needle region, and we found that there was a sudden spike in the distance, informational distance. There was a sudden drop, well here, there's a sudden spike here in the information distance. There's a peak in the excess entropy, and there's a drop in the entropy density. This was expected. This is saying that we are going from chaotic to, in this case, the needle region. But this is not expected. This is saying that really in the border, something special is happening there, something unique. Something that is not in the chaotic and is not within the needle region, is in the border. So we are seeing here something that then we linked to the term of computation at the edge of chaos. And we started looking very carefully at the spatial temporal maps, and we started finding out that there is indeed some patterns going on there. Very interesting. Carol said just a word about it yesterday. We found that there was a zoo of different patterns, and these patterns started traveling in space and time. And then we have the idea that this somehow can be harvested in some way, in some computational way. And this, again, every time you find this is where we publish this work. So what we're seeing here again is when you go here just in the border, you see a spike here in the excess entropy, you see a drop in the entropy density. These are the distance map of all these points just very near the border to see if we could find something peculiar there. And what you see here, it's not very clear, but I hope you can see it, is that just in the edge of chaos, you see very complex distance array. And from there, we built how were the oscillators coupled one with the other. And we found when you are in the chaotic region, nobody's coupled. When you are in the needle, within the needle region, this coupling really doesn't have much structure there. But here, in the border, here, you see a very complex hierarchy of coupling between your oscillators. So you have collective oscillators, which they are not physically coupled, but then they become functionally coupled. And that's a very interesting result. Again, this is published somewhere, and probably the reference is there somewhere. From there, I will go very fast now, because I suppose I'm out of time already. We analyze other type of couplings. This I won't talk much about because this was the talk of Carol yesterday. This is another type of coupling. And what I just want to highlight here is that you find similar results. And that means really this phenomenon we are seeing is not very sensitive to the type of coupling you're having, so it's quite robust. And that's important. That's important because it means that you don't have just to tune very fine your system to get the behavior you're looking for. This is quite robust behavior. So if you have a bunch of oscillators and you couple them more or less without really going into the details of how you're coupling, you can find very complex behavior, and you can find this is what we call computation of the edge of chaos. And this immediately makes us think of something people have been working from the 70s, which are called cellular automata. Cellular automata is a very funny thing. I don't know if all of you know about the game of life. You have your universe adjusted into squares, and you say what's happening in a square depends on what's happening in the neighbor of the squares. And then you have an update rule. And you say, okay, in this time, the square has some number, and depending on how the squares around them, in the next step, it will have another number. And this was a very interesting thing in the 70s up to today. It's the obsession of somebody like Wolfram, the guy who is behind Matemáticas, and because it has very complex behavior. I'm just going to show very fast that here, well, these are spatial temporal of these one-dimensional cellular automatas. And here, the only thing I want to show, and this is something that is known for a while, but again, what we did is we make a quantitative analysis of it using the anthropic measures. Well, you have three types of behavior here. You have a behavior this is the equivalent of very boring. This is equivalent of going to a periodic behavior. And then this is the equivalent of going to something which is chaotic. Well, sorry, omega 4 is the one that goes to chaotic. And then, omega 3, sorry. And omega 4 is the one that is where the banana is, where you have a complex pattern there. And we did an analysis with cellular automata, and again we found things there of complex behavior and something that can be harvested. What's the interesting thing about this? Wolfram found out in the 80s that a very simple rule called 110 was a universal Turing machine. It was a universal Turing machine. I don't have to explain much that because we are a computer conference. That means this is as capable as any other computer. We're looking into it from another perspective. We're saying, if you are a universal Turing machine, you have to be complex enough. And what we found is that from the anthropic measure, that's the case. Those are those rules. You see here, this 110. Those are the rules which are interesting and the ones we are looking into it. And again, this is where this was published. And what we did is, instead of using a discrete cellular automata, we did a nice trick. We say, okay, we're going to consider that our automata is a continuous deformed cellular automata. Again, I won't go into details. You can find it in the paper. What we did is, for example, for a particular rule here, we said instead of going to 1 and 0, you're going to a number which is between 1 and 0 and 1. And this can vary, it can have a variation in the real axis. It can take any number. With that in hand, we again let evolve the system for some particular rules, and I just want to show you that we find these sudden spikes in excess entropy and these sudden drops in entropy density, and that's what we call, that's the fingerprint of what we're saying, that is computation at the edge of chaos. And again, this is the patterns that happen there, and there's an analysis of all these patterns, and you can find that in the paper. And this is another example. This is a more detailed example. Here again, you see the spike here of the excess entropy, and you see the sudden drop in your entropy density. And again, here, quite boring, then start happening some pattern in here, and then you see patterns that start from the initial conditions and they can travel up to the end. And when you go into the chaotic one, you just end up with some dice run. So I won't go into that. Again, you can find here all this that I'm explaining here. You can read it more carefully in the corresponding paper. And then I will end up in how can you apply that. I will start with a very simple example of what we're doing, something right now. This is some result they sent me some days ago, some of my students who are making the PhD sandwich PhD in Germany between the KIT and us, and also some other institutes. And what we are using that to distinguish and to make connections between regions in the brain. You have a lot of sensors in the brain, and then you ask your subject to do some activity, something. In this case, they were walking and they were having a visual stimulus. And again, this is a complexity map, and we could distinguish here. You don't see it very well, the colors there, but here you see the activations of those regions in the brain that has to do with the visual cortex and has to do with movement. And our entropy measures clearly distinguish the bunch of other regions in the brain which are not activated, and those which are activated are just here. And then from that we can make a functional map of what are the regions of the brain which are connected one with the other. But the other thing I want to show you, which it has to do more with the topic of this conference and of this Congress, of pattern and so on, is I just want to say here just a few words very fast, that is the following. Now we have something which we think has computational power. And again, remember, computational power not in the algorithmic sense, in the sense of something which is storing, transmitting, and transforming information. And what was the next thing that we can ask ourselves is, how can we take advantage of that? How can we harvest this capability? So that's a question that's going around in the minds of a lot of people, how to do that. And one of the ways of doing that is, and then I make a big leap to what we're hearing here, you have a neural network. And we couple these oscillators to your neural network to see if the neural network is able to harvest the computational power of these oscillating systems. That's what we did here. Here, what are you seeing? What you're seeing here, this is a Lorentz system, a model of climate, which is chaotic, and chaotic means you cannot make much prediction. And there was a very nice paper, and a very famous paper some years ago from the group of Edward Ott, and what they did was they were using a kind of neural network, so-called reservoir computing network, and they were making, if they were able to forecast how the Lorentz system behaves in time, and without knowing that this is a Lorentz system just from the data, how can I predict what's going on in the future? So they made a very nice prediction up to here, more or less, and this is in what is called Lyapunov time, which I won't define right now, but just take it as a sense of time. And you can see that up to here, more or less, the agreement is quite good, that it's around 7, 8 or something like that. And then from here, there's a divergence between the prediction and what the real Lorentz system is doing. We did the same with a neural network, which is coupled with this, with the things we're doing. And you can see there's an improvement in the prediction. So here you have a prediction around 7, and we go up to around 11. And this also, it's a very interesting thing. This is another kind of system. This is a very interesting equation, the so-called Kuramoto-Shibashinki equation. This equation is how does the front of a flame behave. If you have a fire, when you see it in the films and so on, you have a front of the heating, and this front just travel, in space and in time. So this is how it's supposed to travel this front. These equations try to make a model of that. And this is how, well, this is time again. This is your front. Well, the details are really not important. This is what's going on really. Using the Kuramoto-Shibashinki model, this is what's going on really. This is the simulation made again by the Ott group. And you can see it's quite, and this is the difference. And you can see he predicts quite well up to this here more or less, and then he goes just straight. He just is not able to predict anymore. This is using our models. This is, again, Kuramoto-Shibashinki. This is prediction using the neural network, and you can see we can go far beyond what the Ott group did here. So this is interesting, and it's nice. Here you have a prediction around 6 Lyapunov time. Here you have around 12, so we are doubling there, and we are very happy about that. This is just very, very first steps. We have a lot to do here in terms of optimization and so on. We haven't published yet. And just to finish, this is a group. These are all the nice persons who've been working on all these results. I'm showing you, of course, this is not the work of myself. I'm the boss. They are the ones who know what's going on. I'm just controlling them. So all these are my students. These are my PhD students. And then these are students who are doing master degree or licenciatura, we say in Spanish. So thank you very much. That's all.